Bart. It needs to take a little time
like
for it to propagate across the various different things. But I got a little chat here. I can see what's going on, see when it's live. But Bart, thank you so much. Not just for being here, but also I always ask people if there's any homework that I can do beforehand, and you gave me like this amazing list of stuff that I just got completely lost in. But let's just make sure we're live and everything's working, and then we'll dive into it. I'll get you to introduce yourself and stuff. But I'm just going to check by sending out a message. Hello, are we loud and clear? All right. And we'll see if we get anything happening here. All right. So there's the chat. There's thing.
I see the chat here. Yeah.
You can see. Oh, good. Okay, good. So there you go. Yay! There you go. Thank you, Claire Burr. So there we go. We've already got they're already showing up 5 by 5. Yep, sounding good. Fantastic, Mandy. All right. Well, let's get into this. Bart, thank you. Let's start, if you wouldn't mind, by just letting people know who you are, what you're into, and maybe even where you are as well. Because let's start with you.
Yeah. No worries. So I'm Bart Rood. I'm an assistant professor at the TU Delft, so the Technical University of Delft. And Delft is a small town in the Netherlands between Rotterdam and Amsterdam, our two biggest cities. Yeah. And this technical university, I'm in the faculty of aerospace engineering and in the department of space engineering. And my group is called Planetary Exploration. So we go from technical university to aerospace, space, and what they call a planetary scientist. But my background is diverse. So I studied here as an aerospace engineer. I graduated in satellite tracking. So I think I know how to track satellites, to know where they're flying.
I hope you know. I mean,
I hope I know. Yes. And then did a PhD in geophysics, so a little bit more science, learning about the Earth, about lithosphere, planets, mantle convection, and how to use satellite data, and especially in my part, I'm expert in gravity data, so interpreting gravity data, and trying to map the gravity of Earth and other planets, and to see how and what we can learn from that data set.
Which is amazing to me, because I mean, I sort of fancy myself I know a little bit about a lot of things. Gravity was not something I thought we were measuring. I thought that was just like gravity was gravity. That's, it's like this here, it's like that on the moon, it's like that on Mars, simple as that. So the idea that it was being, first off, measurable, and then we'll get into this a little later, but that it's being measured quite accurately since the 1930s, basically, right?
Yes, yeah. And even earlier on already, that scientists became aware that just like you, I was also when I came out of high school, I thought gravity is one number. In the Netherlands, it's 9.81 meters per second.
That's it. That's what I thought.
That's what you learn.
Yeah.
But already Newton found out that this is not the case everywhere on Earth. And back then, they mostly saw that the gravity changes with respect of the latitude, so where you are with respect to the equator. So the gravity is a little bit less on the equator than on the poles.
Right.
And this
because it's further away from the center. Is that?
Yeah. The Earth is a little bit pressed due to its rotation or pulled.
It's a bit squashed, isn't it? Yeah,
a bit squashed. Yeah. And on the equator, therefore, you're further away from all the masses, and the gravity is slightly less. But if you start to measuring the gravity field even with more precision, you see that locally we also have variations, and that is where my expertise come in, because all those local variations tell something about the mass distributions underneath us. So
how local? I mean, how local can you get? Like, what kind of scale are we talking about here?
It depends on your precision. So what I work with satellite data, this is we now go to, for Earth, we go to scales of 500 kilometers, so really country size or Netherlands size structures. But colleagues of me and researchers I talk to, they have equipment that every kilometer we make a measurement, or even they have measurements that they can see somebody going into a building. So precise. because
So you
you
can
and
see
I
the
are also
change in
mass.
gravity by how many people are in a building?
Exactly. Yeah, yeah, yeah. So it's the
Wow.
best security system ever because you can't trick it. If you're there, it sees you.
Yeah.
So
Wow.
so gravity data really depends on the accuracy, and this is something I tell my students and then people in the public as well. Is if you measure gravity very poorly, you can determine the mass of the Earth. If you do it slightly better, you can determine the shape, the flatness of the Earth.
Mm-hmm.
And by going even more precise, you can learn more and more about the substructure. And the
Interesting.
and the cool thing is, and this is I'm very enthusiastic about. We are now mapping the gravity field for I think 20 years now with satellites, and every month we take a snapshot of the
Mm.
gravity field with high precision. And putting all these snapshots together, we can even see changes in the
Mm.
gravity field. So we see the gravity field on Earth changing slightly.
Mm.
And these are mass transport processes like melting of the glaciers on Alaska, in Greenland,
Right.
Antarctica,
Right.
but also hydrological signals like the Amazonian basin or other hydrological basins.
Mm.
And and the most incredible thing is that we can even see large earthquakes. So the slip event of, for example, the Sumatra earthquake in
Mm.
2004, I believe, and the Fukushima with all the nuclear reactor
Yeah.
issues
Yeah.
was a huge impact, and that displaced some mass, and we could see that with satellites in space.
Wow. So you could
And
actually register the difference before and after
yeah,
the
yeah,
wow.
yeah,
Wow. And you were saying that Canada, my section of Canada apparently is just coming up a little bit. We're lifting up a little bit because is that
exactly.
historically?
Yeah, yeah,
Yeah. Yeah.
yeah. So that was my PhD about, not on Canada, but it happens also in Scandinavia. But in Canada, it's the largest
Yeah.
signal. So previously we had these huge ice sheets. You know, the Ice Age movie.
Yeah.
Earth was covered with this 3 kilometer thick ice sheets, and they
Mm.
melted away, but their mass pushed the Earth a little bit in,
Mm.
like a gummy. You push
Yeah.
the
Yeah.
gummy,
Yeah.
and then you release, and then you see that the gummy goes up again. And same is happening on Earth, and we can measure the change in mass because the crust comes up, so some mass of the mantle need to flow inward. So we
Mm.
see an increase in gravity in Canada. Yeah.
Wow. I can't I can't get my head around how precise this stuff's got to be. And you're and is it better to be gauging this from space than on Earth itself? Like is it as sensitive or more sensitive from space than it is on Earth because you're not being there's no disturbance or
It's that's I can say yes or no. So it is always better to measure something closer. We have
yeah.
the law of gravity. It's made by Newton, and
Mm.
it says the strength of a gravitational attraction, the force, is equal to the masses that you're measuring,
Mm.
and divided by the distance squared of where you are and the
Right.
mass you want to
Right.
measure. So the signal is stronger if you're closer to the mass.
Mm.
So on the ground, that's the best way to get the strongest signal.
Mm.
However, on the ground, we can't be everywhere on the ground each month. And that's
Mm.
where satellites can
Right.
really help. They can cover the Earth within a month almost everywhere. So we
Mm.
can map each time the gravity field.
And how close are they from an accuracy standpoint? The stuff that you're getting on Earth versus the things you're getting from satellites, are they comparable or are they?
Um, yes, yeah, yeah, yeah. So what the also the benefit on in space is that we do not feel that big 9.81. We do feel the
Mm,
changes with respect to that, but
right.
the big acceleration that goes into the motion of the satellite.
Mm,
So
mm,
you can build different apparatus, different instruments between on space, on ground or in space. So
mm.
on ground, you always have to cope with this 9.81, and then variations of 5 to even 8 digits behind the comma. And
Wow.
in space, you can only look at these variations.
Right, right. And what? So just so people have and for myself as well. how are you measuring this? Like, how are there? I know there's multiple different ways of doing it, but are there? What's? Do you have a specialty? Do you have, or do you use them all? And how is it done?
So I try to use all. So I'm not the guy that does the measuring,
Right.
because I leave that to the engineers that are very good at this.
Right.
But I do teach how you measure. And in gravity, you can't do it remotely. You have to be at the place where the gravitational field is. And I teach a lot, so I mention my students a lot, and some of them are watching, I know. So.
Oh, really? Oh, okay. All right. Don't be careful. Yeah.
Yeah. No. So measuring gravity, you always have to take care of two things. You need to have a mass, a piece of a mass that moves. So you need to measure distance and time. So you can make mistakes in both, in the distance and the time, and therefore it's very difficult to do that.
So it's accuracy on both ends of that are important, right?
Yeah. So you need to have a very precise clock, and you need to.
I love it. That's good.
Yeah. And you need to have a precise distance measurement.
Right.
And then the thing is, there are more accelerations on this object than gravity. We have in space, we have air drag, or very small air drag, but still air drag. We have accelerations due to the light from the sun. We have all other kind of accelerations that we have to decouple from this gravity.
Right.
And that makes measuring gravity, even on ground, very difficult. You always have to compensate or calculate or model all the disturbing forces to get this very accurate. And the accurate you want to go, the more accurate you want to go, the more difficult this becomes. Right. And this is where a lot of technology is developed. And so you asked what we are using now. So on ground, I think one of the best mechanical measurement is just dropping a mass. So it's this huge tube. You drop a cube of mass, and you have a laser that follows it, and you do that multiple times, and it has some damping. And we have one at the TU Delft. It costs
it's just
more
a drop
than my
tower.
house.
Really?
Yeah, it's a drop tower.
It's a drop tower. Why is it so expensive? Because of the sensors that are required?
The sensors and all the precision. But you can also
more than my house.
It costs more.
You don't want to live in a drop tube, though. It's just not the same. It's not the same.
I asked my professor, "Can we buy one?" And he said, "No."
No. You have a choice. You can have a house or a drop. That's it.
Yeah. House. I prefer a house. Yes. You can measure pendulums. So the swinging of pendulums. This is what the professor we were talking about in the submarines that will come later in this podcast. He used
golden
pendulums. The golden cap.
Fantastic name. Yeah.
It's an incredible instrument. So the period of a pendulum is proportional to the local gravity. But in space, we can't use that things. We basically use the spacecraft itself. So the spacecraft itself feels the gravity and all the other disturbances. So what we do is we follow the trajectory of the spacecraft and measure all the accelerations that are not gravity. And then we subtract them from each other, and the remaining signal is the gravitational signal.
Wow.
That's in a summary what we do with spacecrafts. And there are different ways to do that.
That requires two spacecraft to do that, or you can do it with one, or
you can do it with one. That's what one of the satellites missions that done that was the CHAMP mission that had an accelerometer on board. Basically, something you have in your phone as well.
Oh yeah.
That measures all the accelerations, and we measured its position with the GPS, and by using the information of its motion around the Earth and all the disturbing forces, you can recalculate gravity.
So it's just changing its position ever so slightly as the gravity changes, and you're measuring those tiny distances.
Wow. Yeah. If there is a little bit more gravitational attraction, it goes a bit up, and if there's less, it goes a bit.
But these are absolutely minuscule amounts.
Yes. It's a few centimeters, sometimes a few millimeters.
Oh, it can be as much as that. Oh, wow. Okay.
Yeah. And this is why I like it, because this links to my master thesis, the tracking of satellites. We have to take into account the motion, and we can do this. And some smart professors here at the TU Delft and in Germany, they said, yeah, this is nice, this satellite, but what if we take two of them? And we put a link in between, sort of a distance measurement. You can do that with radio, or nowadays we do it with laser. And you have this harmonic effect, because say I'm a mountain and the satellites fly over me. The first satellite will feel me first because he's closer. So he will start to fly a little bit faster. So the distance of the satellites, they will increase. Then they fly over me, and then this one feels me, the mountain, and it catches up. So you get a decrease in distance. And then we fly further, and this one doesn't feel me anymore, so it can go
picks
further
up the speed.
up. So that's what we call the GRACE mission, or the satellite.
Oh, the GRACE, yeah. Yeah, they're neat looking satellites too. They're like glass coffins. These are weird.
They have these solar cells on top.
Yeah.
And these are two satellites trailing each other, and basically we measure the harmonic signal they're making. This instrument that you do the whole time, and then also they both have this accelerometer to take out all the accelerations due to a disturbance.
Right.
And we saw this is very good technique. That is better than using one, because we can make this distance measurement much more precise than the distance from a satellite to
right.
Wow. So this,
but it takes two satellites, so that's an added complication.
Right. And this GRACE satellite is very successful because it's not only increasing our resolution globally, but also it can map the changes in this gravity field we were talking. And GRACE, now we have GRACE follow-on, and they're thinking in NASA for GRACE C, so GRACE continuation, and at ESA at NGGM, and together they become the MAGIC mission. That really will give us 30-40 years of data, and then we can really see really incredible things. And I'll talk a bit more about that also when we go to Mars, because this is exactly
because Mars, because that's the other thing, is we don't have to just be looking at our own planet. This applies to all the other ones, and you've made some really interesting discoveries about Mars.
And I'd like to talk a little bit about that as well. But just to conclude the ways we can measure gravity, there is a third way we can do this. This is from the European Space Agency. They call it the Lamborghini in space. It's called the Gauge mission. And this is a single satellite, but it has not one accelerometer, but it has 6 accelerometers. What they measure is not the acceleration, but the acceleration gradient between the two. And they're so precise that they can measure the gradient in the gravity field.
Wow.
And because you have 2, you can the disturbing forces act on both of them. So if you subtract them from each other, you subtract the disturbing forces, and you only leave. You keep the gravitational.
So it's the same technique that they were using on the submarine in 1934, except it's in space.
It's in space,
and the sensors are a lot more precise.
The sensors are so precise. I heard somebody from ESA telling, and I like this story very much. The old Earth observation project manager, and he said the sensors are so precise that if they could measure accelerations, have a oil tanker on the ocean that is moving, and it's full of petrol or water or sand. And if a snowflake would fall on this oil tanker, these sensors were able to see the acceleration of the oil tanker.
Really?
This snowflake. So this is the precision we can currently fly in space.
That's insane. I mean, that's more like that seems wow, because you see these satellite images, and they're always, this sort of a grainy image if you get a rough idea of what it looks like. And it's like, and some of them are quite clear when the military stuff's amazing. This is, wow. So the military must love this.
Yeah. So gravity research is a lot used also in submarines. Because it's the only way to navigate without going up to the surface. because
Mm,
you need to have good gravity maps, but also what they call an IMU, an inertial measurement unit.
mm,
You need to know your gravitational surroundings for the
mm.
IMU not to drift away too much.
Wow.
And I think, well, I think because I don't know what the Navy is doing, but they invest a lot in these gravimeters,
Mm,
because with those technologies you can, navigate underwater without looking outside. You
mm.
can just, yeah.
Now is your Lamborghini in space, is that using quantum tech sensors, or is it using still sort of classical sensors, or is it actually getting into the quantum stuff?
So no, so up until now, Grace, Champ, and Goatje all used mechanical sensors.
Right. Okay. Yeah.
Even Goatje, the one with the snowflake, it
Yeah.
was a cube of mass that was held together with condensators, and they could sense these tiny
Wow.
differences.
So we can get even more precise.
And that's the goal. Yeah, yeah.
That's
So
wow. Okay.
I think you talked to the queen of quantum.
Lisa Werner. She's fantastic. Yeah.
Yes.
Yeah.
Yeah. She contacted me a few years ago to talk about gravity and Mars research we and my group are doing, and I was amazed at what these instruments can do. They're
Yeah.
precise. That is a nice thing, but they're also very stable. And
Mm,
this every measurement is absolute, and
mm,
this is crucial for gravity monitoring,
mm.
especially looking at changes in gravity. You want to have this absolute measurement.
Well, and it fixes both sides of the equation too, doesn't it? Because it can also become much more accurate time as well
Yeah,
as much more accurate distance changes and stuff.
magnitude. Yeah.
Yeah,
Yeah.
it's fat. It's fat. I mean, I got to say, this must be an incredibly exciting thing to be in right now, because all of these technologies are coming together that are just going to vastly improve your ability to do what you're doing. Right? I mean,
Yeah.
between
No,
these, yeah,
it feels like that, and so this technology, I was watching it a little bit, and I didn't really understand. I'm not a quantum physicist,
yeah, me neither.
and I didn't understand. It looks cool, and there are nice YouTube movies about it,
Yeah, there's some great
but
YouTube. Yeah.
yeah, but how can we use this in real life? And then I say real life because I know space research and planetary research is not really real life, but in and
It's
then I
more
talked to
real than
Lisa.
quantum is to me. I
Yes,
gotta
yes.
tell you, I really struggle with that. Yeah.
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 No, and then I talked with Lisa, and Lisa can explain. Well, you've done two shows with her, and she can explain this quantum on a very
Yeah.
simple way.
She
And
was the one. She was the one, I think, who's explaining the Bose-Einstein
yeah,
condensate, which I guess
yeah,
is very useful for you or
yeah, that's the
stuff.
one we need. Yeah,
Yeah.
yeah, yeah.
Um, oh, that's great that you're talking to her about that. Was that just by coincidence? You guys are just in the same kind of world? Is that?
Well, she called or she emailed my professor, and my professor always, if there's something in an email with Mars, he always redirects it to me.
You're the Martian. You're the Martian.
So
That's it.
yeah,
Yeah. Yeah.
this Mars go to Bart.
Yeah. Yeah.
And so I contacted Lisa, and we started chatting and meeting up in conferences. And the more we started to talk, the more we got excited by
Yeah.
combining this new technology and mapping gravity.
I'm getting excited. I'm not even in the field. I like,
Yeah.
it's such a
Yeah.
great, what a great sort of the connection of technologies to have together.
No,
Uh,
really, yeah. And we're trying now also to convince other people,
mm,
especially the space agencies, but
mm,
also other researchers, because on Earth we already know the gravity field quite well.
mm,
Also with Grace C and NGGM, the Magic constellation, those are 4 satellites. You don't need quantum anymore. If you have 4 satellites
right,
to measure the field, you're precise enough.
right.
Your sampling is good enough. And
Mm,
also on the moon, we have from the Grill mission, which is a Grace type of mission, also
mm,
2 satellites training each other. The moon we also know very well, because in the moon we can fly very low.
right.
So on Earth we need to be above the atmosphere, otherwise we burn up. But the
Mm,
moon doesn't have an atmosphere.
right.
And what I like about the Grill mission, and I'm not sure if it's true, but I heard some of the engineers talk about, at the last part of the mission, there were the mission control, the operators of the Grill mission, they had problems because they had to dodge mountains. That's
Oh my.
how low they were flying.
Oh my God.
Yeah. So this was
They're top gunning it. They're top
yeah, they
gunning
were
it.
top gunning with two satellites
Yeah,
trailing each
yeah.
other, and
Oh my
it
God. It's
yeah.
literally.
But this
Wow.
mission, it's not in the news, and it's but this was an excellent mission, and thanks to this mission, we now have the best gravitational map of any solar system body, and
Mm.
that's the moon. And it helps now with this the Artemis program
Yeah,
where
of
we
course.
want to land on the moon. Colleagues of me in Berlin, they are really looking at all the rock formations, water, and thanks to
Mm.
this gravity field, yeah, we learn a lot. So Grill, look it up.
All right,
Also
grill.
thinking
Okay.
that
Yeah.
this is an incredible mission.
How?
So, but also not quantum.
Yeah.
So for quantum, it's very hard to sell to ESA and NASA because they say, well, Earth is not needed, Moon is not needed.
Mm-hmm.
And then Lisa and I were talking. You know what? This Mars is this is the best place to do it
Mm.
because it would quantum would benefit because we're not going to send four satellites there. We can't fly as low as on the moon,
Mm.
so we need a pair with quantum sensors.
Mm.
And well, my group and I, thanks to the InSight mission, this is the latest mission by
Yeah, insight.
NASA
Yeah, yeah, yeah.
that is landing on Mars. We can now build crustal models and use the data that is already available.
Mm.
And we think, we're trying to publish this, it's still in review, but we think that there's still active mantle plume material going up. We
Oh,
see
is that
this in
article still not come out? That's still because
I, yeah, the last time we spoke, I got it back, and it's now in minor revision. That means I still need to do some spelling checks, and one of the reviewers still needs some computations, reviewer too. But
well,
they're really
because it's
helping.
amazing. I told my kid about this as he was going to school today. I was just like, I'm talking to a guy who's with, as my son left, and
Yeah,
he actually stopped for a second and said, "Wait, what?" I said, "Yeah, it's being pushed up. It's being pushed up."
yeah, yeah. So
So
we did publish a few of these results already, and it's in an open archive. So if you want to read it, you can
oh, I
Google it
love
and
the
you
open
can find it.
archive. I got to say, I'm
Yeah,
so sick of paywalls. Every time I try to go and read anything, it's
yeah.
so frustrating.
No, no, but we still want to publish, and I think this review process is really there to get all the essence, all the did you think about that? So
Mm-hmm.
I'm really listening to the reviewers about their points
Yeah.
and trying, and I think we now all three are converging towards a version that is there. But the conclusions I made are still there. So this anomaly could still be there.
Right.
Uh,
Do you want to talk
and
about it? I mean, can we talk about it here? Is that
yeah, of course. So what we use is we use again the gravity data that we already have. So
mm,
I told you, you can already get some gravity data by looking at orbiting satellites, and we have
right?
a few of them now in Mars.
Right.
So researchers at JPL, at Goddard, in Berlin, and Roma also. They
Mm,
made these gravitational models by looking at these satellites. So we have gravity, and thanks to the MOLA instrument, which was the Mars Orbiting Laser Altimeter,
oh yeah.
we also have very high precision topography data. So the
Mm,
shape of the, and
right.
those two data you can use to combine in certain physical models
Right.
to build a crustal model and even look at what we say mantle convection or mantle flow.
Mm,
And
mm,
my students and I, we combine these two type of models, so crustal models and mantle convection models,
mm.
and you tweak with the parameters, and then you try to fit the gravity and the topography data.
Right. Right. Try to
And we
line them up.
yeah.
Yeah.
You
Yeah.
play with the knobs and you see it goes up, and then you play
Yeah.
this knob. It's a bit like that, but then the computer does it all. It's millions of models, and
Yeah.
then you hope it fits. And we see that with all the models that fit the gravity and the topography, we can't explain only with a crustal model. We
Mm.
can't. It's not possible by tweaking the parameters we think are important to
Mm.
explain the gravity.
You're seeing differences between the
Yeah,
measurements.
yeah,
Okay.
yeah. But by adding a mantle plume, an upwelling underneath Tharsis,
Mm.
then all the parameters align, and we can model
Wow.
exactly what we observe, or almost exactly what we observe. So it is plausible that if you trust our models, that there is this possibility of a mantle plume.
That it's actually pushing up. on the
Yeah.
mantle.
Yes. Well,
And in a specific
yeah.
region too. It's a specific region. It's
Yeah.
where the volcano is, right? Isn't that it's where the
Yeah, yeah.
main
So Mars has basically two regions that are highly. They have big volcanoes. That's the biggest one is the Tharsis region. This is a region that looks like a little bit of a dome with a big set of volcanoes. Mons Olympus is one of the largest
right, the big
volcanoes.
one, yeah.
The big one, the biggest, the size of France volcano type. And you have Elysium. This is where InSight landed. So they also looked at
Oh,
first
right.
mission.
Okay, yeah.
But we concentrated on Tharsis because in the gravity field you really see a concentration of something there underneath this region.
And you're seeing more than just what you see on the top on the surface. You're seeing, okay, got it.
Yeah,
right.
and this is and we tried because with gravity it's ambiguous. You can always tweak your model such that it fits the gravity field. But what we try to do is to keep the physics as is and just play with the parameters with the physics that we think can explain the model. And
right.
That is a bit abstract, but it's like Occam's razor. To keep your model as simple as possible, if that can explain the observations,
right,
then the chance is that you're correct.
And you can compare it to this great data that you've got on Earth.
Yes.
And see what the differences are there. So when I say you're seeing more happening, in a way, you're seeing less, and you're seeing less gravity because it's further away from the center. Is that wow. That's pretty neat.
Yeah.
What you read this stuff and I'll put a list of the stuff you gave me to read in the show notes because there's just so much fun stuff there. It does start to become kind of intuitive. You start going like, oh, okay, that makes sense. Like that's why we can figure out because there's just, I just didn't realize that we were figuring out what planets were made of and what was happening under them with gravity. I just assumed it was all, some kind of chemicals or light.
You need chemicals. You always need chemicals.
It's true. It's true. Yeah.
In any form.
There was just science happening.
No, exactly. And well, I'm fortunate that I chose this topic and gravity field modeling and planetary gravity fields. And there are some really nice scientists out there in history that made these theories that we are now using to explain planets. It's not local. You're not looking at a small patch of your hometown. No, you're looking at the system, the planet. And that allows us that these theories were made on Earth, which is a very special planet, but still a planet. And we can apply them to all these other type of bodies, the planets in the solar system, but also moons. And even now, I checked last week because I had to do that for my lecture. We almost now know that there are 6,000 other planets out there in other solar systems or stars.
Wow.
So, and this is just a fraction of what we think is out there.
So
by understanding the planets, understanding how they form, what are their engines, we can learn about the universe, about how life is. Why is life only on Earth, not on Mars or on Venus? Why is Venus so different from Earth? They're the same size, they're the same mass, but Venus looks like hell and Earth looks like paradise.
Right? Let's keep it that way.
Yes. Yeah. So for me it's why I wake up and come to work. It's
fantastic
story. Yeah.
Well, and also I love the fact so you're also able to go because another technology that I'm guessing is going to be helping you out is the AI stuff, the machine learning stuff, because you're going to be able to process large amounts of data. And as long as you understand, if you give it the right understanding of what to look for, it can find patterns in these massive amounts of data that might be more difficult for us humans, right?
Yeah, and this even has a personal story. So AI is for me. I'm not a computer scientist, and I do a modeling. So it's a sort of AI. But my dad is a IT profession. He was there when the internet started. He put Java on the internet. I'm not sure if that's a good or a bad thing, but he taught me the power of information, computing information.
Yeah, my dad too.
And I think, and he showed me that he already did AI in his bachelor's. I was not even born yet, but
Really?
he did.
He was
He did
doing
it.
AI during the AI winter?
19 well, it was before mine, so 1980s,
Oh
1982.
wow, wow.
He had this bachelor, and it was a neural network that controlled a sensor for water level. That's very Dutch. You want to know where
Ah.
your water
Yeah,
level
it is
is.
very Dutch. It's true. Yeah, yeah,
And he built a neural network sensor that could decide, should I turn on the pumps or not. That
yeah.
was his project. But
Mm,
that was basically what we are now doing with these language models. It's a neural network that learns from the inputs and produces outputs. And his
mm.
conclusions were back then, and that I really find, he said we need more memory because otherwise
Yeah,
the neural network. And I think
that's it.
that's why we're now getting to this boost of
Mm.
he's talking. Leo wrote, that's my father.
Oh, it's your dad. Oh my God, your dad's
Yes.
watching too. Hey, there you go.
I told him to watch it.
Hello, Leo. Uh,
No, but he was right, because back then we didn't have big memory slots, and
oh, I
now
know.
we have.
Memory was. I mean, the hard drives were
Yeah, yeah,
kilobytes.
floppy drives.
No,
You have the
they
what?
were megabytes. Was
Yeah,
the
yeah,
big
yeah,
ones
yeah,
back in the day.
yeah.
Yeah, my
Yeah,
father
so,
was running his medical office on a Commodore 64
wow.
back
Yeah,
when it was seen as a toy,
yeah,
basically.
yeah,
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 yeah. So
yeah.
he got me all excited about it as well. Yeah, it's good
Well,
old dads.
yeah. So I always laugh a little bit. Oh, we have these new AI things, and blah blah blah. The only new thing now is that we just have more memory. Back
Yeah,
then,
yeah.
the mathematics, the computer programs, they
Mm,
could do it, but the only thing they were not accurate enough is
mm,
because of the data,
yeah.
because of memory.
Huh.
And nowadays, so I'm still not the AI expert, but I was a few years ago at a conference where all these geophysicists come, and I was held up by a woman, and she said, "Can I work together with you, because I really like this Mars concept, gravity, and but I'm an AI expert. I try to find patterns in gravity, and then try to do something geophysical about it."
Mm,
And I thought, oh, that would be cool, but what can we do? And there is this problem in gravity field modeling, is that we don't really have depth sensitivity. So
mm.
if you measure the gravity above the surface, you can't really say, is it coming from the crust or is it coming from the mantle?
Ha. Okay.
And this is called the Neumann ambiguity. I think it was Neumann or one of these others.
Okay.
And you can mathematically show, if you have one gravity point measurement, you can't distinguish between a shallow source but a very small mass, or a high mass but deeper.
Hmm. So you can't tell far away from close up, basically.
Yeah,
Yeah,
yeah, yeah, yeah. So
yeah,
far away heavy, or close up light.
yeah, yeah, yeah.
That's
It's like a
there's always
Father
this.
Ted. It's like a Father Ted episode. Yeah.
Yes,
Okay.
yeah, yeah,
Got it.
yeah, yeah.
Yeah.
And this problem, we gravity field modelers know, because the seismologists always tell this, and they say gravity, you can't do anything with it because of this
Right.
problem.
Right. Okay.
It's a bit more nuanced, because if you have a full field with different resolutions and spectra, you can
Mm.
already start to do. But with gravity, you always need to constraints.
Right.
And I
Right.
told her, can we tackle this problem? Well, not tackle, because that is mathematically impossible, but can we, with some constraints, see if we can be able to see what mass or what variation, what kind of information is coming from the crust, and what
Mm.
kind of information is coming from the mantle.
Mm. So by giving it enough data, it
Yeah,
might find a pattern that says, "Oh, usually when that happens, that's more mantle than crust, or vice versa."
exactly. Yeah, yeah,
Interesting.
yeah,
Oh,
yeah, yeah.
wow. And are you
Exactly.
doing that? Are you doing that now?
Yes, yeah, yeah, yeah. So, and that is also really nice. One of my first master students, when I was a WELAS, I was supervising as a PhD. I was supervising master students, and he said, I want to make synthetic models. I want to
Mm,
make planets that look real but are not real.
mm.
So he devised some mathematics on that, and we coupled that to my code, and we are now able to make planets that are synthetic, that have the same kind of information as Earth, Mars, Venus,
Oh, wow.
but they're not the same. but we can also vary that. So we can make millions of realistic planets, millions, trillions, whatever. How much memory do you have? And we can train a neural network. I think she used a neural network or an inference. I don't know. This is details.
Okay, fair enough. Yeah.
But she trained some artificial intelligence model, and we gave that model the goal of selecting where's the information coming from the process.
Based on these synthetic training data basically that you've created for it,
where we know what the variation, what the information is coming from. We put it in there, and she showed that she was successful, and she's now finishing her PhD thesis in Glasgow, and we'll
Glasgow,
yeah. And it's not so. We do put a few constraints on there, some physics in there that help stabilize the problem. But she applied it on Mars, and the results that are coming out of there is very interesting. But
even if it just tells you where to look, like even if it just says like, hey, there's something going on here, we think it's this. If you can verify it, it's just more data for the model, so the model gets better and better and better at this stuff.
Yeah,
that's amazing. But that's not out yet. That's
no.
Coming soon.
It's coming soon.
Okay, got it.
In theaters.
That's in the
summer.
The Bart Root sequel will be. That's the next one. Okay.
Yeah. No, but that's what I like about science is that people come to you and I have an idea and can we work together? And then this magic starts to happen. And
I say there's always a nerd who knows a nerd. I say
yes.
Because whenever I need to find something out, there's always someone who knows somebody because of Stargate and because of the interest in science that I think surrounds a lot of science fiction. I mean, the real science fiction, not the fantasy science fiction. Is that I feel like there's always someone out there who's doing something that sort of pertains to it. That's amazing. So when do those findings come out? When do you?
So I think she will present some of them at EGU. That's the European Geophysical Union. That's next week in Vienna.
Oh, really? So we got to keep an eye out for that. Okay.
Yeah,
all right.
Yeah. But then she's finishing her PhD thesis, and then hopefully we'll also write a paper on that chapter.
That's great.
That will take X amount of months.
Right.
But yeah, all these puzzle pieces we try to use the gravity in different ways than previously, and I think AI there can help. It's not that AI is the big solver, but it can help in finding new patterns or finding get inspiration in maybe we can use this in different ways. I think she showed this.
The sheer amount of data. I mean, I think I'm going to get you to. I think unless there's more you want to talk about. I mean, there's a lot to talk about Mars, I'm sure, but I'd love to go back. There's a wonderful history element to this that my mom will love this part because she's a big history buff. But there's this wonderful. Well, it's so funny because this is what I love about doing these chats is that it's not just about the science, it's or the engineer, the engineering or it's the people who do it, because I think it's this weird connection that people have these weird mixes of things that they're interested in. And I think that that's a whole part of what makes this stuff work and what makes you look for connections in other things. You looked back and were so taken with this 1934, was it? Submarine trip. Which just sounds like a movie in the making right there, myself, frankly.
There was a movie made about it in
was
1930s. Yeah.
Wow. Because, I remember Das Boot being pretty terrifying. I can't imagine a 1934 submarine. Oh, God.
No, it's not as Hollywood-ish like that movie, but one of the officers, the first lieutenant, brought a camera with him and made pictures of the whole
I've seen that.
Yeah.
Oh, so there's actually documentary stuff about it.
Yeah, well,
that's cool.
It's sort of. So he filmed it, but they edited it such that it was like a sort of a hero movie. It's slow. It's 1930. But I talked to a lot of people, and they said you could go to the cinema and watch this movie.
Really?
really something.
That wasn't in your list of stuff, though, was it? I saw clips of stuff, but I didn't see
Clips,
an actual.
yeah. But you have to go to the Dutch National Archive.
Oh,
I
yeah.
could try to find the link for you, but
That'd be fun to see.
They still have. So it's called back then it's called the Polygon movies. So Polygon is basically that makes all these old movies.
Oh, interesting. All right. Well,
But
you should tell people what this is about. So what is this? What is this that we're so excited about?
Yeah, so when I was doing my PhD, again, I was sitting next to the professor, and the professor, before, just a few years before I started my PhD, was in this TV program called in the Voyage of the Beagle, in Behind the Voyage of the Beagle. And this was a Dutch television show where they put scientists on a sailing boat that followed Darwin, basically. So the trip that Darwin made, and every week they had an episode or a part of the voyage.
I remember this, yeah.
Yeah, and it was excellent. I loved it. We watched it back home, but they picked not only Darwin type of science, so biology, but any type of science that was there. And my professor Bert Vermeersen was in the piece that they sailed from Mauritius to New Zealand. Sorry, to Perth, to Australia.
Perth, okay, right.
Yeah, and he explained gravity basically, because gravity has an effect on the oceans. It can make it higher or lower, and that was it.
I guess that makes sense. Yeah, if you got and also you've got the deep stuff.
If you have more gravity, it pulls more water, so you get a higher in the water level. If you have less gravity, it will.
Yeah.
So the oceans are not really smooth, but they are dented. This is called what I think, thanks to the people in Potsdam, the Potsdam potato. So if you look at the Potsdam potato,
because it's got little pucks and marks. Yeah, that's great. That's great.
And that's basically the shape of the oceans.
Great.
Of Earth.
But you've just reduced the beautiful oceans to a potato.
A Potsdam potato, yeah. But they're very proud of it, and I think
fair enough.
They did excellent work.
Yeah.
But because he was in the show, he was always asked for this heritage type of questions. But back then, he was busy building the group that I'm now part of, Planetary Exploration. So he said, "Bart, you're doing something with gravity, right? You take this." So. And this was a project, was about a Professor Vening Meinez. Never heard of him. And I was like, but it's about submarines, gravity. Have a look, go to the project group. And these were heritage people and historians. And they needed a scientist or somebody who knew things about gravity, a geodesist, to explain them the text that this professor was. And I went into his books and I became addicted. This story of this professor is incredible. And we focused on this K18 trip, but he's done many of these trips around the globe using a apparatus that could measure for the first time with high precision the gravity field on the oceans.
And this was called the Golden Calf.
The Golden Calf. Yeah, it's this golden-ish pendulum apparatus.
It's beautiful. It really is kind of beautiful.
Yeah. I always told, because I last Friday again, but I give a few of these public lectures where I talk about the Golden Calf. And there is a myth about the name of the apparatus. It could be because it was gold, people called it the Golden Calf. But there's a second story that I like the best, and I say let's choose that one. Not very scientific, but
history is written by the winners. Yes, exactly.
And it was that Vening Meinez needed to have at least as much possible vibrations as possible. Sorry, my English.
No, it's good. All good.
No native speaker. So he asked all non-essential crew in the submarine to lie still in their beds. They could read, but they couldn't move. So all non-essential personnel, still the steering persons, they could stand and move. but the Dutch Navy thought back then that was a deprivation of life joy, I think, if I translate it to English. Deprivatie van levensvreugde in Dutch.
Right.
And
they're depriving them of life joy. Yes.
Life joy, because these measurements took 15 to 45 minutes each, and he took 3 per day. So yeah, that's quite a lot of time.
It's a nap time. I
would
wish
say,
I could have that. Yeah.
But the high officers in the Navy said, no, this is... So every sailor on board these expeditions got 1 guilder extra per measurement in these trip wages. So more paycheck.
Nice.
So these sailors, when they saw their golden calf taken into the submarine, they thought, Professor Vening Meinez is sailing with us, and it means we get more money.
We got the golden calf. Oh, that's great. That's great.
I like this message.
Yeah, that's good. That's good. I mean, it definitely. I would buy that story more, because it doesn't. I mean, there's gold involved. It looks gold, but it's more of a this wonderful steel. I mean, maybe you could explain the mechanism, because that's also fascinating. Just how he figured this out.
I think I sent you a YouTube movie, but
it's fantastic.
YouTube movies, but try to Google golden calf or Vening Meinez.
I will put the links in here for sure. Here we go.
Perfect. We have made this animation, and the problem is with the pendulum that if you measure with a pendulum on the oceans, the whole apparatus swings a little bit due to the motions of the
waves.
A
lot, depending on what you're...
Yeah. Well, on 30 meters depth, the waves are a bit...
I guess that's true. Yeah, you're right. I'm thinking on top, not beneath the surface, right? Yeah.
And so he had to come up with something to again, remove the disturbance from the actual gravity measurement. And that again, it comes back in every historical gravity measurements. You always need to think about the disturbance to remove them, to actually get an accurate gravity field or a gravity field measurement. So what did he do? And he took 2 pendulums, let them swing opposite to each other, and then subtract and then measure the distance between them. So meaning he could measure the both swinging, but because they were swinging opposite each other, he could subtract the accelerations on both pendulums. And this made it him possible to only, or to separate basically the motion of the ship from the gravity.
There's a wonderful, if you want to look at the I wonder if I could show the video at all.
It might be possible. Can you share?
I might be able to. Let's see. Concept of measurement. Let's try. We'll see if this works or not. I'm very good at messing this up, so we'll see. See if I can do this. I'm gonna go over to tab. Let me find it.
It's the concept of measurement.
You know what? I might do this later, because trying to find the way to do it.
And people, you posted the links. And,
I put the links in there. It's fascinating, because the measurement between it gives you this shape that can then be turned into exactly what you're what's left
and then
over,
you see basically the eigenmotion of the 2 pendulums, and Vening Meinez showed the mathematical derivation that this also relates to the gravity, and then you could subtract these measurements. And that's basically the whole apparatus. So the apparatus are basically 2 pairs of pendulums. He has 3 pendulums, so 2 pairs. Because the geodesist doesn't measure once, always twice.
Right, very good.
How well you are, you always have to measure twice.
Okay, yeah.
And he made a lot of efforts to make the rest of the environment stable. So there's a protective cap on it, so the temperature, the air pressure, everything is equal. Which I find this is very fascinating, is he had these mirrors on top of the pendulums, and then he put a light ray on it. And via some mirrors, these light rays were captured on photographic paper on a dark chamber on top of it. I think
really?
I have a few of them here. So I hope you can see them. You see
look at that.
Some of these measurements. You see the pencil markings of this. And then what
they're getting that from that's literally being like that's the paper's just reacting to that.
Yeah, so this is typical photographic paper. And then he had to, in the submarine, while it was moving in the dark, because if there's light, this becomes black. He had to develop them, and then just like a photo, you got basically.
Oh, I can't even think of that. Of course, you can't. You've got to do this in pitch darkness, otherwise you've just destroyed all of your.
Yeah.
Wow.
So
they've got rolls and rolls of these things. They've saved all of these rolls.
Yeah.
How long are they going to last for? Are they going to deteriorate? They must.
Yes. So we at this project we were also looking at, can we digitize these rolls, because there might be still useful historical data in there, and we're still trying to get some funding to really digitize all the rolls, because there are hundreds, maybe even thousands of these rolls. They all need to be, well, they are the size of 2-3 meters, something.
Yeah.
This, and they need to be scanned and photographed and then digitized, and so this is a huge.
Could you video it? If you videoed it, could you not? Could that not? Because then
maybe
you just roll it in front of the camera, as opposed to having to take.
Yeah, I found another device that is sort of a photo device, but it only makes a line photo, and then you scan it and you roll it over the.
Oh, like a panorama type thing.
Yeah.
Yeah.
You could use that, but again, time, money. It's a really nice historical project. And, back then, we were mostly looking at describing the science and the things, but we found all these rolls in the depot down in several depots spread around the Netherlands.
But you're missing one. There's one trip that you're missing.
You saw my first video.
I'm telling you, I did my homework. I did it all. I watched all of it. Oh yeah.
Yeah. So the rolls of the trip, the K18, they are missing. So I have a lot of rolls from before this voyage and a lot of rolls after this voyage. But I do not have them of this trip that is very special for me.
And you've no idea why they're not a part of the.
We have some ideas. So back then, Indonesia was still part of the Netherlands. It's called the East Indies, and it might be that the geologic and geophysical departments had them there. But then the Second World War came, the Japanese came, so it might be that they're just destroyed, because also the submarine was sank during the Second World War.
Oh no, really?
Yeah. So in the Netherlands,
with the equipment.
No. Vening Meinez was
okay. All right.
But the submarines they are from the Navy, so they were used in warfare and in defense. And in the 1941, I think, the Japanese came so close to Surabaya, where the submarines were hosted. The commander back then, not the one that sailed with Vening Meinez, but the one that was responsible then, he sank the submarine.
Oh wow!
Then the Japanese, from using your technology. But then the Japanese, they resurfaced it. They took it from the bottom of the ocean or the sea, and they used it as a radio station in around Surabaya. And then the British torpedoed it again in
right.
1954. So it's now on the bottom of the ocean, close to the ports of Surabaya.
But unlikely that the rolls were still on board anywhere.
No, not on board. But I think 80 years is a lot of time to have things gone missing. There's also Vening Meinez during the World War II. He was director of the KNMI, which is the weather system of the Netherlands.
Oh, right. Yeah.
And he was responsible for all the data. There are some documentation that everything of the KNMI, all the data, was taken by the Germans towards somewhere in the north of Germany, captured by the enemy. And I found letters from Vening Meinez and other KNMI directors asking after the war from the Germans to get it back. And some has been placed back, but I've also seen in the letters that not everything. So it could be that it went missing, it's gone, but it might be still somewhere in a German archive. And we really tried our best to find these ones. It was my personal, but there are many possibilities. So it could be in Indonesia, could be in Germany. It could even be because in that area where the archive was, it was liberated by the Russians. So it could be that the
Oh my
Russians.
God! So couldn't be thinking about. Oh wow! Yeah.
So
and it's data, right? So they don't know. It could be worth. It's yeah.
Yeah, and there's even a possibility, and this is something I want to work on the coming years. My historical part of me is that Vening Meinez had a very dear friend called Harry Hess. This was an American officer in the American Navy, and he was also a geophysicist. And Vening Meinez did a lot in the East Indies, Indonesia, measuring. But Harry Hess, because he was a friend of Vening Meinez and he learned a lot, it was really his mentor. He was able to also use the apparatus, the Golden Calf, to use it in American submarines and measure the East Indies, so the Caribbean.
Oh, wow.
So we have very nice gravity, very old. Well, one of them is here. This is the Indonesia gravity map. It's the first gravity map of Indonesia.
Wow.
But you also have one of the Caribbean, and that was Harry Hess. And why I like to study that, because the golden calf is replicated, I think, 5 times. Three are lost, 3 or 4 are lost, but there's one in one of the museum in America. I always forget which one. But one in one of your science, or in the American Science Museum, there is the golden calf somewhere displayed. The original.
All right. So if anyone out there is in a museum and sees this fantastic, what is it called? Would it be called a gravimeter? Or?
A gravimeter, yeah, pendulum apparatus.
Right, yeah. So if anyone sees it, send us a photo so I can show Bart. So now the other thing that, sorry, yeah.
Yeah, just to conclude, so it could also be that Vening Meinez sent the data to Hess. Or to his American collaborators. Vening Meinez was collaborating a lot with Americans. So it could be that it is also there.
And there's no way that there's just too many things to do in the day to try to follow up on all of these. That's kind of a fun mystery to solve, wouldn't it?
Yeah, I do. For history, I asked my professors, can I do one history project per year? And they said yes. Okay, yeah, it's related to gravity. Right. Yeah. And last year I had a very unique other project also related to gravity, but that's finished. We published the book. Did I send you that?
No, I don't think I got that.
So we found a dissertation from 1830. Where a Dutch scientist or a PhD student was measuring the shape of the Earth using gravity data. And
cool.
He referenced Newton and Huygens because back then they were the scientists.
Wow.
And but the dissertation was in Latin, so we found a translator and we revived it, but it's in Dutch because the translator said my English is not so good, so I have to translate it.
That's fine. Translation. You know what I did? I translated a bunch of stuff just using Perplexity AI of some of your stuff. There was some of the transcripts were in Dutch, so I just had it translated into English. It was actually very, very good at it. So
I think the translators are now very good between English and Dutch. Latin might be, but we really wanted to be sure that it was correct. And even for him, it was difficult because he was specialized in classical text, Homerus, Odyssey, things like that. Or that's Greek.
Not the scientific text, which is
not a whole scientific text.
And that's the problem that's the problem with transcription, isn't it? It's like you need to have a certain specificity to your knowledge. Because like trying to translate a medical thing is very different.
Exactly.
Yeah, that's interesting. Although
at least Latin is a dead language. I could help him. Yeah.
At least Latin's a dead language. You don't have to worry about Although I guess there's probably localization elements to it as well, doesn't there? This is what I love about this is that we're talking about gravity and spacecraft, and we end up in the 1930s looking for rolls of paper. I mean, this is there's a wonderful show that I used to watch as a kid called Connections, which was this old, I can't remember who it was who did it, this old scientist folk guy who would just go like, did you know that because of this happened? Or, and it was just, he would make these wonderful connections crossing history and time and stuff. And this just sounds like the perfect example of it. How long the trip was a very long trip, right? He was on this sub for quite a while.
Yeah. So Vening Meinez was, it started in November 1934, and They came in Surabaya summer 1935. So 8 months.
Yeah. In a
He took
1930s submarine.
submarine. Yes. Yeah.
That.
So
Oh
so
God.
in the Dutch language we have two words for a submarine. Well, we have three words for a submarine, but all the
Mm.
Navy people say the first one I can't use. So duikboot, which means diving boat.
Right.
I can't use that because that means you only dive once. That's a diving boat.
Oh God. It's a
So
sinking boat, basically. Yeah.
yeah.
Yeah. Okay. Got it.
But
Yeah.
as a kid, you always say submarine is a duikboot, is a diving boat.
Yeah. Yeah.
And the second one is called an onderzee boat. It's an undersea boat.
Undersea boat. Yeah. Yeah.
And then you have the third word is onderzeeër, and that's more translated submarine, under the sea,
Right. Right.
goer or
Right.
something. And the undersea boat, the boat is the one that has been riveted. So it's a submarine, but it is a riveted submarine.
Mm.
And the onderzeeër, which is like the nowadays the current submarines, that is welded. So
Yeah.
it's welded together.
Yeah.
Uh,
I'll
that's
take the
where
welds. I'll take the welds over the rivets any
yeah,
day.
the welders they can go much deeper.
Mm.
Onderzeeboten, the ones of Vening Meinez, they can go maximum 100 meters, and preferably safe distance is 30 meters.
And so they were 30 meters basically most of the time. Is that that was the goal?
No, they were most of the time on the surface, and then when in warfare there was something to happen, they dived and then did their thing and then came up again. And
Oh,
also
really?
with
Wow.
Vening Meinez, basically the only time they go under the water was when he had to make his measurement.
Oh, wow. Okay.
Yeah, but back then, but with the onderzeeërs, so the welded submarines, they stay more underwater than above.
Yeah. They're designed more for that, aren't they? Yeah.
Yeah, so you see the technology has an effect on the operations of
Wow. And the other thing that I loved about this, there's a wonderful sort of interactive map of the mission where you can go through each chunk of what they were. It speaks to elements and it speaks to locations. But one of the things it talks about was that it was God. What have I now? I can see if I can find it because people should look at this for sure. It's interactive website, Gravity Expedition C. There you go. Got it. God, I'm telling you, your homework was fantastic.
I think the link is expeditionwikipedia.nl.
That's it. I've got it. I'm putting it in right now. Yeah, definitely check this out because you can click on the stuff. It sort of opens up and it has all sorts of stuff that was going on. I've forgotten what it was that caught my attention. But if you go through it, it's this wonderful sort of series of locations and also just some of it'll touch on things like different areas of the sea when they get to this, like there's a trench. So they want to make sure that they get that. Is that what is the trench what you've got above you there? Is that the same one or is that?
No, but this is Indonesia. So the end of the trip is coming around here in Surabaya. No, the trench is between Africa and South America, close to the equator.
Right.
It's called the Romanchi Trench, and it's one of the places where the two continental plates or the oceanic plates rub against each other. It's called a transform fault, and it produces these huge gorge. This one is 7 kilometers deep, with a lot of earthquakes and volcanism associated with it.
But I love
back then, Vening Meinez was not a believer in plate tectonics.
He didn't believe it until
no.
Yeah.
Well, never. That's I think also.
Well, he never changed his mind. He never changed his mind.
No,
really?
No. And this was because you had the believers or the fixists and the mobilists. So the mobilists, they thought the Earth was moving, and the fixists they said no, the Earth is rigid. It only buckles, but it doesn't tear or.
So they still believe things were knocking against each other, but they didn't believe it was actually shifting.
Yeah, because plate tectonics is only accepted by the whole community in 1967.
That's a year before I was born.
Yes.
This has only been accepted as long as I've been around.
Yeah. And the thing is, Vening Meinez died in 1966, so he could always be a non-believer.
He died a happy non-believer. Look at that.
He died a happy non. But and this is why I want to research a little bit more on Harry Hess. because Harry Hess is a major figure in the plate tectonic acceptance, because he wrote a paper on what spreading ridges are. These are these regions where two plates, they spread out of each other. You get a little bit of volcanism. Iceland, for example, is a spreading ridge. And all across the Atlantic Ocean, in the middle, you have this spreading of the two plates. And we have correspondence between Vening Meinez and Harry Hess discussing this concept, because here on this map you see also these gaps. There is volcanism there is these seismicity. But if you look closely at the gravity signature, it's different from a spreading ridge. And this is what Harry Hess saw, because in the Caribbean you also have subduction zones. But he also measured these spreading ridges in the Atlantic Ocean, and he saw the difference. And Vening Meinez, he should have seen it, but I think because he was a fixist, and the whole Dutch community was a fixist, he didn't believe in plate. He didn't believe that the plate could tear and sink down. He thought it would buckle and buckle and buckle. He was a typical civil engineer. He says the plate is strong enough.
Interesting. It is funny how science is shaped by, or even obstructed by, people's preconceived notions on how this stuff goes. I read an amazing book on the guy who discovered prions, which are these basically self-replicating proteins in the brain, and no one believed. Everyone's like, no, that's impossible. And because of that belief, they just refuse to look at this. And it's so funny how you sort of forget that science is still about humans. It's still about how humans are dealing with this stuff. So
and exactly this point I want to study, because I think if Vening Meinez was a little bit more open-minded, Harry Hess was a friend of him, but he was a younger scientist. Vening Meinez was back then already an established professor.
Right.
So and it seems to be, if the older you get, the professor is the more stubborn you become.
Right.
I'm very over.
It's funny, isn't it? It's not universal, because I've definitely know a lot of older professors who aren't that way. But yeah, I wonder what it is. Is it, maybe it's just the ability of the elasticity of the brain, perhaps?
Might be. Yeah. No, so I want to study this in the concept of the relationship between Vening Meinez and Harry Hess, because Harry Hess did change his mind. And he wrote this paper that was one of the papers that was used to accept plate tectonics. The big one was the magnetic stripes, and all that's the major work, and that is really. But I always think, what if, and we now have this Marvel what if show. What if Vening Meinez was a little bit more, because he was earlier than these magnetic anomalies, so he could already see in his data that there is a difference between spreading ridges and subduction zones. So you need different mechanics, and he didn't do that. And I want to understand why Harry Hess did and Vening Meinez didn't.
You know what's interesting though too is, I wonder how much of it is the fact that so much of this was done by hand. Like so much of this required, you had to sit down and work out stuff yourself with like pen and paper or pencil and paper. And so you're only going to do that if you think you've got the right handle on it. Whereas nowadays you can have models that will show you, like, you can sit back and not sit back. You have to work with the data, but eventually you can sit back and see and perceive what's going on. Whereas then it would have all been about, scribbled little equations and little drawings and stuff. Right. So
exactly. And this is with the instruments we build, but also with the data analysis. So I'm practically a data analyst.
Yeah.
So I
think we're all going to become data.
Yeah.
I think it's all, that's
the computer makes us.
Every scientist I talk to spends most of their time in front of a computer now. I mean, and what I love about the AI tools is that it's opening up all of a sudden, even, someone like myself who's I've always loved computers and programming and stuff, but when I actually want to get stuff done, it was always problematic. I still needed to get someone to do that. Now I can have it work out these little programs for me and get things done with them. I love the idea of applying this to science. I've got entomology friends who spend a lot of time looking at videos of spiders and things. and to document what it's doing. And the idea that you could then that they now have the tools to, in plain language, write an application that can monitor this for them and look for what they need. It just opens it up. I mean, I just think the kind of discoveries we're going to get going forward are just going to be massive, because there's
No,
just
exactly,
it's opened it up
exactly,
to
and
lots of people.
it keeps it removes the scientists from their garage where they're
Yeah,
sitting to the public space. Where here at the TU Delft also we have a lot of these public citizen science projects where
yeah.
citizens with their tools can help scientists
Oh,
collect data, but even interpret it.
I
There's this
love that. Yeah.
yeah, in NASA, they did this incredible thing with the Juno images,
Hmm.
where they asked the public, look, we have this beautiful camera, but we don't have the time to look at the data. Can you guys make these beautiful images? And we now have immense amount of beautiful images of the clouds of Jupiter, of their moons, and I think the agencies and the universities should use this tool, because computers make it, and the software make it easier to help out with going
Mm.
through all the immense amount of data.
Yeah, like crowdsourcing some of this stuff. We've seen it in the film industry as well. I remember when Xena Princess Warrior was a big
I
thing.
know. Yeah, yeah, yeah.
They used to hand out um like elements of the footage, like that had lots of the cables and stuff, and they'd have the fans would get the scenes, and they would paint out
Wow.
all of
Yeah,
and of course their work is fantastic because they love the show, they want it to be great, and they're
yeah, yeah.
doing it just out of their out of their appreciation for the show. So
Excellent. Yeah,
that's very neat. I've got some
yeah,
questions for you. If you got some, we've
yeah, yeah, yeah.
I have, I think, monopolized your time for long enough now.
No worries. I'm here for you.
All right, Hexaverse. And by the way, huge thank you to Agna for making this all possible, and also
Thanks,
for
Nathan.
handling our questions here as well. Hexaverse asks, is gravity linked to meteorology at all? That's mine. That's mine. LOL. I love meteorology. Taught it to myself since I was 5. Meteorology and gravity.
Yes, yes. So the thing is, I just gave a lecture on physics of planetary interiors,
Hmm.
where my part is gravity modeling. And I showed this type of rocks, which is a meteorite. So I think it's that type of meteorite or meteorology. That's always I confuse. But let's assume it's meteorite.
Go with meteorites. Okay. Yeah. Yeah.
So the meteorites they help in assessing what kind of rock material we have. So
Right.
what kind of rock we could assume is inside planets, and then we know their density. We can convert that to mass, and then check, is this composition working or is not. So
Hmm.
so yeah. So meteorology, but if it's meteorology with atmospheres and climate as well. So the atmospheric changes, so the density of clouds, and we can measure effects of the atmosphere in the gravity observations. We even
Really?
have to correct for it, because otherwise it would obscure more into, signals for us. So
Wow.
atmosphere scientists use it a lot, and this is also the mission I'm trying to work towards on
Mm.
Mars. We will sense the gravity field,
Mm.
so study the subsurface and the volcanoes. But at the same time, we're measuring the atmosphere and the climate on Mars. So
Mm.
you get that science for free. So a gravity mission is more than only gravity. It looks at also the disturbances, which is, for
Mm.
example, the atmosphere.
Wow.
So a colleague of mine used, he's now working at KNMI, the meteorology of the Netherlands, and he used the Gauge satellite
Mm.
basically to understand what are the winds at 200-kilometer height in the atmosphere. So
Oh.
he looks at how the satellite is pushed by winds,
Oh,
and
wow.
and he sees by looking at the disturbances, he can make this atmosphere
Interesting.
model and this unique data, because we didn't have any ideas that there were winds there, and
Mm.
his PhD and now his work is on making these models, and yeah.
I
And
mean, that something that keeps coming up is the idea that we have this data. We're able to look at it in so many different ways now. Like, we seem to be getting almost as many new discoveries from the old data that we have sitting
so,
around.
Yeah.
That's very cool. So
Yeah,
so
and it's the noise of one man is the signal of another. So
yeah,
this is
there
in
you go.
gravity. This is the case. You have to get rid of the disturbances, but it means you understand the disturbances, which
Mm-hmm.
could be data for somebody else,
I
and
love
therefore
that. The noise of one man is a signal for another. That's
I stole
fantastic.
that.
Oh, I love it. It's great.
Yeah,
That's
yeah,
great. It's like
yeah,
it's like one man's trash is one man's treasure, basically, isn't it?
yeah, yeah, yeah.
Um, all right, Raj Luthra. So okay, so Hexiverse was asking about meteorology, so it was about weather, right? Is that right? Did I get that
Yeah.
right? I always get my ologies mixed up. Thanks, Hexiverse. Good question. Raj Luthra asks, oh, a bunch of questions. What has been discovered by measuring gravity from sea and space? Can this help develop artificial gravity technology in some way? Artificial gravity. Wow. Okay.
Good, good, good. So just to be clear, I'm a Newtonian gravity expert. So
Okay.
I ignore all Einsteinian effects. I know that they are there, but they're so small that we can correct for them,
Mm,
and they are not really interesting. From a physics perspective, yes, but we understand the physics. So when we
mm.
understand something, we can correct for it.
Right. Right.
So I really look only at changes in gravity due to changes in mass.
Right.
So if we have, and then try to understand how to interpret those gravity from mass. So what I do is I learn to interpret gravity, not so
Mm,
much as how is it created, or if you
right.
talk about Higgs fields and things like that, you have to ask Lisa or somebody else.
Okay. All right.
Me is really the Newtonian gravity, the gravity that is generated by mass. So
Right.
if I would, if you would ask me, can you generate a artificial gravity system? I say, well, a planet, use a planet because it's
It's
there.
already got it. It's
Yeah,
already built. Yeah.
or
Yeah.
I have some high school kids that came to me because again, yeah, gravity. You're a gravity expert, but I'm a special gravity expert.
Right. Right.
But they looked at artificial gravity and they looked at spinning
Right. Right.
systems, and you can do the dynamics. We learned that here in aerospace. That's one way of creating artificial gravity. But you get sick if you walk around. So
Oh, yeah.
that's more for the.
I get slightly motion sickness just talking about it.
Yeah.
The whole. I'm such a wimp on that stuff. I
Yeah.
don't. I
But
don't.
but what we learn, yeah. So we learn about the planets. We learn about processes of the planets. Again, earlier in the podcast, Grace has given us such a unique data set, a monitoring of the gravity changes.
Mm,
We can see the melting of ice sheets, and these are used in these climate models where they say, okay, the ice is now melting, and we can really see acceleration just by looking at the gravity. So
mm,
acceleration in melting of Greenland and Antarctica.
mm,
We
mm,
can see that Canada is rising, and how fast they are rising together with the gravity field data, we can tell something about what we call the viscosity structure of the Earth.
mm,
That is how viscous the mantle material flows around each other. And
mm,
that tells us something about what it is made of, but also how warm it is. So the
mm,
temperature, the thermal characteristics.
mm,
And that has a lot of implications. We can look at where volcanoes start. We can learn about how the Earth forms. Why is it still so hot?
mm,
What kind of process is there? And some unexpected things, like Grace found these earthquakes. So we can study earthquakes. We can study droughts. We can study atmosphere.
mm,
Droughts is basically mass transport. So everything you think of mass that is transported, we
mm,
can study with
mm.
Earth. There's
Fascinating.
even this excellent story by ESA. The Gochi mission flew over the Sumatra earthquake when it happened. This devastating earthquake with the big tsunami in 2004.
Yeah. Yeah.
And they could measure the shock wave in the atmosphere that produced a bubble of the atmosphere that Gochi was flying over. And we
Wow.
could basically have a seismometer in space by
Wow.
looking at the influence of yeah, the atmosphere.
So could that be used in detection then, or I mean,
Yeah. So some of so ESA is really putting a lot of effort there, and a
Hmm.
lot of scientists as well. Some of my colleagues in France, they look at this part. So can we use monitoring with gravity satellites
Mm.
for early detection of gravity of earthquakes? And I think that this is why GRACE C and NGGM and the Magic mission are there. That it's
Mhm.
really becoming a monitoring service for the public
Yeah.
to
Is
um,
this data public? I mean, is this data available to people?
Yes, yeah. So both NASA and ESA, I think they have this declaration that after 6 months of taking the measurements, they have to give it back to the public.
Right,
So
right.
that gives some time for the scientists that put a lot of investments, money, and time in there to publish their results,
Yeah,
and
yeah.
then it's open and for me to use, for you to use, to look at patterns.
Mm. So you
And
could technically, so the citizen scientists could Xena Princess Warrior this by doing some of
exactly.
their own
Yeah,
stuff.
yeah,
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 interesting.
yeah, yeah. No,
Um,
this is, and I think the holy grail is really to predict earthquakes. And there
yeah.
are some ideas, but this is still we need better measurements
Mm.
and really
Well, and
like
then
this is
combining the different ways
yeah,
we have of
yeah,
predicting them eventually.
yeah.
Yeah, I mean that
Yeah, and
really is.
some earthquakes seem to show a precursor, so a signal just before the earthquake in the first few days before the earthquake
Oh,
that there
really?
is a change in gravity, but
Oh,
it's still
wow.
in the noise level. So we're
Yeah.
not sure if this is so to be continued. But I think with the new missions, more data, more precise data is coming in. Yeah.
What is your preference? Do you like the Earth stuff or do you like the Mars stuff? I mean, obviously you like them both, but is there like if you could just focus on one thing, or is it the history? I mean, that's
Ah,
what.
you're asking somebody who has too many projects.
Oh, so you like them all? Okay, fair enough.
I,
Fair
I,
enough.
I like the gravity stuff. So the Earth is very interesting because first of all, it's our planet.
Yeah,
We want to understand our home. So
yeah.
so that is, and we have a lot of data. So
Hmm.
gravity, as I told you, gravity alone will never solve anything. You always have to collaborate with other researchers, constrain your models
Right,
such
right,
that gravity becomes important.
right.
So on Earth, we have so much interesting things to do. Also, Earth is unique because it has plate tectonics. So you have all these cool, yeah, physical processes that we
Hmm.
can study. Mars is interesting because the more I study Mars, the more I'm amazed. I was
Hmm.
back in the days. I thought Mars is cold. It's dusty. There's
Cold
some
and dead. I
rocks,
mean, it didn't.
cold and
Yeah,
dead.
yeah.
And the more I study, there used to be oceans on Mars. There used to be big volcanic events. We see maybe even evidence of a big tsunami because of an impact crater.
Oh, really? Wow.
We see in big salt domes. We see a lot of cool tectonics. I think Mars is really proving to become more interesting in the coming decades.
Mm,
We're
mm.
going to see really a lot of cool geological effects and how we start to understand why Mars is different than Earth and Venus and
Mm.
Mercury. And we just need more of these data sets. Yeah.
And are there plans to get further afield than that? Like, I mean, are you gonna get good gravity measurements of Venus or any other planets? I mean,
Well, for Mars, I'm now the lead proposer of one of the M-class missions with a big international team. We're trying to propose to ESA for their M8. This is their. Oh, my wife is calling. The M8
where are you?
mission.
Come
Yeah, where are
home.
you?
Yeah, yeah,
You need to cook.
yeah, yeah.
Um, there is the proposals coming. The deadline is mid of May, and we're trying to set up a proposal where we show, look, gravity for Mars is needed because of this, and this, and this.
Yeah, yeah.
So this is my personal goal now to help these scientists and myself to really show gravity to Mars, and you can help as well. Talk to any ESA or NASA
Yeah.
representatives. Gravity.
Mention gravity every time. Got it.
Gravity, gravity,
Note to
gravity,
self. Gravity, gravity, gravity. Got it.
gravity Mars.
Yeah.
But we try to see what can better data, more data help in understanding the Mars. And I think this is. And My colleagues, they are diverse in. So my colleague across the room is a PI of an experiment on the JUICE mission going to Jupiter and Ganymede. We will learn more about that system together with the Europa Clipper of
What is a
NASA.
PI? I saw that in front after your.
Oh yeah, PI is principal investigator. It's basically
Ah,
the science boss.
got it. Okay, all right. Yeah, I wasn't sure what that was. Yeah.
Yeah,
Oh, more questions. Oh, sorry. I should. Well, I keep stealing you. Sorry.
yeah.
Okay. Can this help in discovering? So this is Raj Luthra again. Can this help in discovering life on other planets? Ooh, I don't know. That's interesting.
Good
If
question.
there's people moving around, if there's,
Then exactly. So it can't, I think, directly detect life. You have other techniques for that, but we can understand the concept of habitability. So what kind of environments are out there that could be habitable? So by understanding your planet, your environment, you can better understand where life could have or will have or is present. And this is where my group is working on. We don't really look at detecting life, but looking at habitability of places. So the question, would there be life on Mars? So currently, it's unlikely, I would say. Not on the surface, but maybe in the past. Colleagues of mine look now at Enceladus and at Ganymede and at Europa, where there's this subsurface ocean underneath the ice. There might be oceanic life there. And I saw last week they found on a exoplanet some signatures in the spectra.
Very specific. It sounds
Very specific,
pretty good, doesn't it?
And that's interesting. So from a scientist perspective, yeah, this is awesome news. But we need to check if that signature is linked to life, and what is the habitability of that particular planet.
If it's just a molten lava of, there's not a lot of,
then maybe there's another process that can explain. So it's very crucial not to only look at the signals of life, but also to look at what is the habitability of these planets? What are the conditions? What's the temperature, pressure, composition? Is there an atmosphere or not? Why is there an atmosphere or not? Look at Venus. We thought it was this lush jungle Yoda type of planet. But, it was covered with clouds. The Russians landed, and it's hell on Earth.
It's hell off Earth. Yeah, exactly. Yeah, that was amazing. That was I was stunned by that.
It was an incredible picture. Yeah. So to answer the question, no, but we can help these scientists to make their claims more solid. So
you're part of the puzzle, basically.
We're building the foundation.
Can you find out what the planet is made of?
Yes. Yeah. So
absolutely.
If you know the density, so the mass, you can check that with your gravity. So what you do is you make models, you assume certain compositions. For example, you look at Earth. This is a peridotite. It's a mantle material. You put this in the lab. You find out the density and all the viscosity, and you put that in your numerical model, compute the gravity, and then see if it fits for other.
Does it match? Wow!
And usually
you can. That determines. That will tell you. That'll tell you. That's what that is.
It gives hints. So it gives hints of it could be this density, and then if you know the density and you know that the elements have a certain mass ratio, you can say, okay, these crystals or this type of material is more likely to be.
Right.
So on Mars, there's still debate, and if some of the other scientists of Mars are looking, they might disagree with me, but in our studies, we see that the Martian surface has a density of slightly higher than what other researchers are saying. So we say that the Martian crust is even holding more iron than previously thought.
Oh, really?
That's by using how we use the gravity and we're still debating, is this true? Is this really, our models say this is true, but again, is my model correct? Is the data correct? And what are the differences between the other scientists? And I think this is science. You keep on discussing, you keep on saying, no, you are wrong, no, you are wrong, and then you try to to come together and say, okay, it's this, and it takes time, it takes discussions, but I like this.
This is why it's so difficult in the social media world to do science, because people you can spit out a lot of absolute nonsense very quickly, but it's very hard and time consuming to do really good research or data. So this is fantastic. All right. How are you doing for time? You got a call from your wife.
I'm here.
Okay. All right. I don't want to eat into, bedtime for the kids or anything. So
no.
Are you posting the data and discoveries on social media? Are you big on social media? So that's a complete coincidence. I just asked about that, but
I used to I was big on Twitter, but
I used to love Twitter. Yeah,
but when it became X, I stopped a little bit. I tried the other parts, but I also then became assistant professor, and I work too much, so
who's
then
got
I
time?
don't have time. Yeah.
Where do you post your stuff?
I post a little bit on LinkedIn, a little bit. I'm still trying to find some system that works for me. For now, I use LinkedIn because that is work. But
and the website? Do you have a website? I'm assuming the university's got a website for.
Yeah, we have different, several different. I have a blog, I think, on Blogspot. I used to write little blogs on science. I stopped doing that again because I'm too busy doing other stuff. But so it used to be Twitter. Now it's LinkedIn, and YouTube apparently.
I love YouTube just as a source of information. I find it absolutely fascinating. But yeah, it is difficult to know what I haven't found a platform yet. I basically just use social media as almost like a marketing tool now, because I used to have wonderful chats back and forth, and it's still good. I find it connecting me with people that I outside of my realm of my film and TV realm. It's nice to sort of talk to scientists and stuff, but it is
and I see when I give these interviews or public lectures, I see that people really are interested in gravity, but also that they hear things that they've never known about, which for me are that's basic knowledge. So I am thinking of making these short movies on YouTube just to explain basics of gravity.
Oh, cool!
Looking at a set of gravity. But
if you need any help with that, I'm happy to. I'm sure we've got. If not me, I'm sure there are other nerds who would be more than happy to help that. I love the stuff you were doing in the history museum with the golden calf. That's just so much fun.
I had help of the media center here at the TU Delft, and they are excellent.
It just brings it to life.
Animations and so. If somebody is out there that wants to put some time in visualizing my stories, I'm all ears. I can talk hours on this stuff.
as I'm making you do right now.
Yeah. But I can't do Adobe. I can't do movies. I'm very bad at picking which color looks nice. I still use the rainbow color scale.
Right. Yeah. I too. I think I prefer talking about this stuff than actually having to try to figure out how to construct the video side of it.
But there are some awesome people out there that can do very cool stuff.
Well, so we'll put if you're okay with this, I'll put your LinkedIn in the show notes as well, so people know where to find you. And of course, the university's online, and they've got a lot of information there as well. Can gravity data help propulsion technologies in some way? Understanding how to escape it, how to escape gravity. Maybe,
we know how to do that. So that's astrodynamics. My other colleagues are doing this.
Right.
So again, it might, but it's outside my realm of gravity. So if you could some way manipulate the Higgs field or something, or manipulate, then you could do it. I've seen the science version of the warp drive, where with some negative mass you could build a warp drive. Again, this is outside my
I know, the faster than light. I'm getting more and more depressed about the fact that we may not get this faster than light thing going.
There's enough cool stuff in the science.
It's true. That's very true. Well put. Okay, Agnes got some more questions for us. Brian Moon, who by the way was very kind and actually just donated some money, did some, I don't know how this even thing works, but yes. Brian Moon, thank you. Do you think gravity might have something to do with the possibility of the universe being a massive black hole?
No.
I've heard this theory, and I've got to look into it more because it's kind of fascinating.
Yeah, exactly. Again, outside my expertise, but I read up there's this, I think from Leiden, which is one of the other towns close by. There's a physicist who has this theory that we are all what's it called?
Like a simulation?
Simulation
theory.
A
Yeah.
hologram.
Oh, hologram. Oh, wow. Okay.
Yeah, right. An hologram, also a projection of reality. And the physicists tell me it's correct. All his mathematics are correct. For me, this is too difficult to
yeah, I find that difficult. I also worry about the implications of that. You know what I mean?
Yeah,
like if we start believing we're just a hologram, then
again, it can, but I stuck at the Newtonian description of gravity.
Fair enough.
And there's so much to do already there that there are other much smarter people than me that can tell.
So black hole gravity is a whole other thing.
Because in Newtonian you would just have strong gravity and it could go to infinite mass, but with the connection between space and time, you get a curvature that breaks time, I believe. So you can't go to so high density because you just break space time. And for me, that then means
it doesn't help you.
I can't study the object, so why should I look at?
That's true. So Stardust Aeroscape says, I guess Bart must love the tidal movements on the Jupiter and Saturn moons.
The tidal movements or the title?
Tidal, Tidal, tidal. I guess there's actually. I didn't even know that was happening.
So this is basically where my group is best. I'm a little bit of a loner on that side. I do Mars, and they say Mars is boring. We should look at the Jupiter system.
Yeah, you're turning into the old man. The other planets. I just stick to Mars.
No, but exactly. I said my colleague Dominic Dirks, but also colleague Marco Vira, Stephanie Cazot. They all work on this. These icy moons, these icy bodies around icy and rocky bodies around Jupiter and Saturn. And why are they interesting? Because before we visited them, we thought they're small, they're far away from the sun, they should be frozen solid. They could have ice, or they could have. But when we came there with Galileo in the Jupiter system and with Cassini in the Saturn system, we saw that these moons they were active, they were dynamic. Io is the most volcanic body in the solar system. Europa has more liquid water than on Earth. Ganymede has these beautiful stripe patterns and incredible geology. When we go to Saturn, we have this very tiny moon, Enceladus, and it spews geysers of 200-300 kilometers. Where is this heat coming from? Where is this energy coming from? And this is where tidal dissipation is coming from. So my professor and colleagues and a lot of scientists, they look at how the moons move around Jupiter and Saturn, and each revolution they are squished a little bit. You can do the same physics by clapping your hands and do a Mr. Miyagi.
Oh yeah.
And you do rip, you get warm hands. This is basically the same is happening with these planets. Or these moons. They move around their host planets and they're squished all the time. This is called tidal dissipation. There's some other astrodynamics I know for the theorists out there, but that's basically where the heat is coming from.
Wow.
And this heat, this completely changes our understanding of a planet that gets heat from the sun, maybe some radioactive heating, and we need to rethink all our models. And this is now the whole topic in planetary sciences. That Io is squished so much because it's rotating so fast around Jupiter that all its water is gone, and it's still producing a lot of sulfur volcanism.
Wow.
Europa is a bit less, so not all the ice, but most of the ice is melted, and Ganymede is farther away, so there's only a little bit of water. And for Enceladus, the same thing. It has this squishing, and it spews out energy. Wow. One of my students, and he's graduating next week or 2 weeks, and he's then starting his PhD on this. He looks at Triton, which is a moon around Neptune, which is the farthest place we can go planet-wise. Okay, I know Pluto is a planet, not a planet, but that's the moon around Neptune.
Yeah.
And they made pictures of Triton, and they saw not a frozen, cold type of impact-related body like the moon. Oh, they saw a moon with a lot of dynamic activity. Where's this heat coming from? Well, it's again this squishing by Jupiter.
Mm-hmm.
The same with the New Horizons, flying even further, looking at Pluto. They also thought Pluto was frozen. And
That was always the image, wasn't it?
And the image that come up there, for geologists and it was almost romantic feelings.
No, it's fantastic because I look, I don't know anything about this. That's entirely new to me. I mean,
Yeah.
but it makes
Yeah.
complete sense. And when you talk about when you're looking for life, can gravity help? Yeah, because if you see a planet that's being, heated beyond.
There were some theories that this would happen, but only by going there, only by flying your spacecraft into the system and do measurements for gravity, but also with your cameras. You can really observe what is going on. So people always say, why should we do space exploration? Why do we put so much money, which is not a lot of money? In the Netherlands, we put more money in beer than in space engineering.
Yep.
But that said, by flying toward other places, we find unexpected things happening, and we learn so much more that we might and usually are applying back on Earth.
Yeah, the technology does come back, doesn't it? I mean,
technology and the science, both.
Yeah.
They are changing our minds. They are changing how we think about being here. Yeah.
I like to think that it's the first green tendrils of Earth reaching out to other places. Right now, they're kind of robotic claws, but eventually there will be little green tendrils as we go. So, time for a couple more questions.
Yes.
Okay. Do you watch any sci-fi and play video games? This is not a question about Stargate. I'm not asking you if you watch Stargate. I'm just
you know this. No. So, and I hope he's still there. My father and my grandmother, they were super sci-fi fans. If you look at the libraries they have, so I was brought up as a kid with Larry Niven, Asimov, all these things. My first book was A Gift from Earth from Larry Niven. I think.
Wow!
It's one of the best sci-fi colonization type of things. And when I was, I think, 8 or 7, we were still debating on this. My father came down with a VHS tape and he said, "Son, you're now old enough to watch this." And we started watching Star Wars.
Wow!
I've grown up with Star Wars, and back then I wanted to become an astronaut.
Right.
And back then you could only become an astronaut by becoming a jet fighter, a fighter pilot.
Yeah.
But there's a height limitation. You need to be below 180 because otherwise you don't fit in the aircraft. And you're 2 meters tall already.
You're too tall to be an astronaut?
I'm too tall to be an astronaut. And each time ESA proposes this astronaut application, I look at all the boxes you have to tick, and I tick all. I have a PhD, but I'm too tall. And this year, or 2 years ago, they had a height exclusion. I was like, yes, but it's the lower height. You can be smaller, but you can't be higher than 180. So then I had to change my career path as a teenage boy, and I thought, well, heck it, if I can't fly the spacecraft that are designed now, I'm gonna start designing spacecraft.
Yeah.
So I started studying aerospace, and then found out that you need to be smaller than 180.
You got to build bigger. You got to build bigger spaceships. Yeah.
So let's do some science, and this is how I. Science fiction is very, very much in the light, because I think it's a way to play around with ideas. What if we had this technology, or what if we had this process? What could we as a society or as a person do? And most of the large ideas in space engineering, look at the geostationary orbit, were made by science fiction writers.
Yeah.
So it's yes, it's fiction. Yes, it's ideas, but it could help.
It's someone once called it the dreaming phase of engineering. It's that first preliminary stage. But there's other. I had a email correspondence with another older professor who was saying that he's concerned that we live in this dream, that because we see all these wonderful things in films and TV now, we're not as enamored with the real stuff that's out there, because the real stuff is not as exciting. I remember showing my Tech Bandits kids a moon Mars landing. I think it was Perseverance landing on that, and I was like, oh my god, isn't this amazing? They're like, yeah, whatever. And I was like, of course, because they've seen this, but there was a laser battle and a ship crashed, and you know what I mean. The reality is, he's worried that because we live in this world where all these dreams are made reality all the time, that we're going to lose interest in the real stuff, which I thought was interesting.
There might be people. So for me personally, I think there always will be people that see the beauty in the reality.
Yeah.
My same dad that was inside or is in sci-fi always. We just watched Mickey 17.
Oh yeah. Yeah. Oh my god, the 3D printing stuff just had me in stitches. Yeah.
But he also was the person that showed me the first images of these landers on Mars. And he showed, Bart, these are images by a robot made by humans of another planet. And you just saw rocks, right? Red rocks. And he was so excited that I became excited. And it go back to those images and go back to the Venera, the Venus lander. You're looking not at Earth, you're looking at a other planet.
I know, it's extraordinary.
From a spacecraft that we build as humans, and the data sent by radio waves and transported by bits, and somebody else on a computer makes this beautiful image, and we can almost touch these other places. This is
we're drilling holes. We're drilling holes into Mars right now.
In fiction, and by this is so exciting as well. And maybe I would say even more than science fiction.
Oh, good. I prefer that. I like that. I like that theory better. Any video games? You play video games at all? Were you doing any Kerbal Space or?
I tried. I was in the beta testing a little bit.
Oh, were you? Oh, yeah.
I was a student, but then I did. So again, I told my dad was in the beginning of the internet. So we had computers where we hooked up our Ethernet cables and we could game against each other. So,
you got LAN battles, right? Good.
Yeah. So Duke Nukem 3D. Doom. But also multiplayer and Command and Conquer and things like that, and other games. I played a bit of World of Warcraft, but then I got a girlfriend and I had no time.
Yes, that's right. Yeah, it's hard to compete. we did a lot of Minecraft. My son and I did a lot of Minecraft together because I just loved, it's like virtual Lego. You don't have to pick it up after. It's amazing, So, okay.
No, and my inspiration is in my office of sci-fi inspiration. So.
The Millennium Falcon. Look at you.
Yeah, this one. So that is I bought that when I had one of my first paychecks or last year, because it was the inspiration for me to really go into aerospace. The Millennium Falcon is, I think, the most beautiful spacecraft.
Yeah, I agree.
My apologies for Stargate, but I also like Stargate very much.
No, for me it was Star Wars. It was Star Wars for me too. You know what I mean? It did the Kessler run in under,
of course.
No, absolutely. I always joke that I wanted to be Han Solo, but I ended up being C-3PO. Because I'm a much better coward and a complainer than I am a hero.
Yeah.
So
I most of my time was Chewie. I had long hair.
Oh yeah. Yeah, exactly. Yeah, Chewie.
No, but
that's right, because you're also 2 meters tall.
Yes, yeah. So I was Chewie.
All right. If we ever go to a convention together, I'll have to go as C-3PO and you can be Chewie. Yeah.
Perfect. Yeah.
There's another question here from William. Hello, William. William Moran says, is Earth gravity conditions unique, or could there be another planet with similar gravity somewhere in our galaxy? I guess.
It's basically, if it has the same mass, yes. So Venus looks a lot like the gravity on Earth. So it's a little bit smaller. It's a little bit less mass.
Right.
So Venus is already a place where you have almost identical gravity. Except there, the surface is very hot and the pressure is very high. So gravity really depends on how much mass do you attract. The thing is, if we now look at the planets that we see as exoplanets, we tend to not see the size of Earth, the size and the mass of Earth. And that I don't think is because they are not there, but our technology is not yet able to see them. But there are So James Webb is getting
Yeah,
there, but
yeah,
still not yet
yeah.
high resolution enough. But
Mm,
there are some ideas to get to telescopes and systems to start to see these smaller planets.
mm.
Because they're so close to the star and they're small, then it's very
It's
very
hard to
difficult
see.
to see.
Yeah,
Yeah.
yeah. But they're going
But
to be, those images are only going to get better too, aren't they? I mean,
yeah, yeah. So gravity, yes. The big question is: are there planets with plate tectonics? Because there are some
mm.
ideas that plate tectonics can only happen if there's life, or life can only happen with plate tectonics.
Really?
Because
Why?
plate
Why the
tectonics,
connection?
yeah. So some researchers say that we can only have this slipping of the plates when we have seashells between them, so dead animals. So
No,
you can only have
really?
plate tectonics when that. Some researchers say this, and
Oh,
the
that's
other,
kind of cool, though.
it's incredible. When I heard it, I was like, yes, this is cool.
I love it.
Uh, other researchers say that plate tectonics create an environment and habitability for the surface that's just right to have this
Mm,
stable climate, this stable, and it can cope with external factors. So
mm,
due to its motion, it's recycling, it can be a very stable and therefore a long time very
mm,
stable. And that's also an element that you need to have life
mm,
evolving. You need time. You don't only need
mm,
liquids and heat and composition. You also
mm,
need a lot of time, because
mm.
otherwise, if you don't have that, yeah, life can't evolve to.
Is it possible that it's so it's possible it's not just a Goldilocks zone within the solar system, it's a Goldilocks planet and potentially even a Goldilocks planet at a certain time in a certain time frame, potentially.
Exactly. Yeah, and the Goldilocks zone is a very rudimentary way of saying which place is habitable. It's
Mm,
it's
mm,
made by astronomers, and they look at the concept: you have a planet, you have a sun,
mm,
and how much energy comes into the planet. But
mm,
already we now know that radioactive heating due to minerals in the crust, but
mm,
also this tidal effect, can create regions much farther out from the star that are
mm,
habitable.
mm,
So yeah, and they depend on time. These tidal dissipations, they need to be in a certain configuration. They first need to evolve towards there, and then you have this time that you have this nice heating.
mm.
So yes, time is really essential, and we're starting to understand this yeah, how other processes can help understand what
Mm.
places are habitable.
Well, and of course, we only look at things. Well, not only, but we struggle to look at things outside of our own lifespan, right? So the hundred or so years that we get, if we're lucky, is such a tiny portion of time compared to a lot of these things that
Yeah,
I think we struggle with the idea that it's going to be there's more going on. Because I mean, you think about it, my even just my view of the planet since I was a kid has gone from a static planet
yeah,
to a constantly moving. I mean, you talk about the Earth
yeah.
observation stuff. They're talking about watching, erosion and things happening on a geological scale. I mean,
We have a GPS antenna on top of
mm,
our laboratory on the roof of our faculty, and it's now there for 8 months. We
mm,
can already see the movement of the European plate with respect to the absolute. So we
wow.
see these drifts of this plate, and I live on the plate. I never noticed this, but
Yeah.
by measuring precise and absolute, you can see these kind of motions. They're just happening. Earth is not fixed; it
Yeah.
moves, and therefore thinking that other planets are fixed is
Mm,
it's Mars is not fixed. We have
mm,
Mars crates.
yeah.
Venus is not fixed. We have volcanoes, maybe active volcanoes on Venus.
Yeah.
Why would the other planets be fixed? Even the moon. I'm now working with people on the moon. They look at the surface, at the interior. The moon is much more than a rock that was bombarded by
So you're seeing movement on the moon
asteroid.
as well?
Yeah, yeah. Well, in geological time. So you
Mm,
see these mare, and you see why this is happening. What kind of processes that generate these kind of terrains,
mm,
um, and they are even some observations that think there is a magma ocean in the depths of the moon.
Oh,
So
wow.
there is liquid molten rock moving a little bit around, but very deep in the moon.
Wow.
And we can see that by how the moon is wobbling through its orbit.
Right, right.
So this is still more to do and more to discover.
What do you? I'm going to let you go soon because I've kept you for almost 2 hours now, and it's just been amazing. I feel like I could do 2 more hours, but
We didn't talk about isostasy even.
I know.
Maybe for next time.
Would you want to touch on that now? Is this? I was going to say, are there any? What are you most excited about looking? In for things to be working on. I mean, do you have any specific things that you're excited about coming up?
So I'm excited at all the missions that are going to come in realization. So space missions. So the JUICE and Europa Clipper to Jupiter. They will completely change our mind about the planetary moon system.
Yeah.
Bepi Colombo, the Venus. There are 2 missions to Venus.
Yeah.
It's golden age. It's
Yeah.
golden age for planetary scientists and their students. So I tell my students as well. In so many years, I hope to see some of these missions fly around the moons. But you guys are the ones that will operate. For the mission I'm working on, the launch is expected 2041. I'm
Oh,
not retired.
wow.
I'm
Wow.
not retired, but I will be gray
Right.
all around. So it's them, it's the young scientists now that we need to make enthusiastic about this mission, because they will be the people that look at it.
And keep them funded, because this is
Keep them
important
funded,
stuff to know. Yeah,
And
very much.
it's not a lot we're asking, right? In the Netherlands, we put more money in producing beer than in space engineering, and I would say
that seems crazy to me.
We should do that.
I mean, I like a good beer, but that's I'm not. I think I like space better.
I like a good space mission as well.
Yeah, no, I agree absolutely. Okay, so and what is what is the name of the mission that you've got going in?
Yeah. So together with Lisa, the queen of quantum,
she hates me for calling her that. By the way.
I know. That's why
That's why. Yeah. She's good. She's fun to tease. Yeah.
Yes. And so it's the MaQuIs mission. She is. So I'm a Star Wars fan. She's a Star Trek fan.
Yeah.
There's this rebellion group in Star Trek called the MaQuIs group, named after a rebellious group in France. That was a rebellion during the Second World War. Was called MaQuIs because MaQuIs is the type of bush that was in that area, and they were hiding in
oh my God, that's great.
And we thought, because it's the Mars quantum interior structure explorer, so that makes a nice.
Yeah, no, it's fantastic. I swear to God, the part of all the fun of becoming a scientist has got to be just naming stuff.
Yeah.
Which my character.
The name is Lisa. I'm bad at naming, but the name is excellent, and people tend to start to know about MaQuIs. And I even was caught up by somebody at ESA, and he said, "Hey Bart, do you know about MaQuIs?" I said, "Yeah, I know a little bit about it." And he said, "Yeah, this is new mission to Mars concept and blah 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 and quantum technology." I said, "Keep on saying this to everybody."
Yeah, well, yeah. So how? So 2 questions.
Yeah.
How how do you go from watching the VHS of Star Wars to measuring, to looking, to peering inside planets in our solar system? What was
step by step?
Yeah, little steps.
Little steps, and I was not thinking of doing that when I saw Star Wars, but the more you study, the more you start to know what you want to do, and you make step by step. This is my expertise, and this is what I want to do, and then you try to aim for the highest. And in my field, that is a mission towards another planet.
Yeah.
And I tell myself, this is a big adventure. The possibilities that I will be putting that mission around Mars is almost zero, but it's not zero. So I do all my best to get this mission to Mars.
And how do we help you make that happen? What can people do to help make that kind of stuff happen?
Talk about MaQuIs. Talk to people that are talk about gravity. Gravity is still this part of science that is a little bit underrepresented. I know.
Oh my God! I thought it was done. I thought we were done.
It is done. We know
Yeah.
everything falls down.
Yeah, that's
That's
it.
it.
Yeah.
No, it's a few of us around the world. I know them all personally that are actually working on gravity field modeling, and
Mm-hmm.
I'm still young and not that long in the field. So we're a small community. But
Mm-hmm.
as I hope I conveyed the last 2 hours, is we can do a lot of science with gravity observations.
Mm-hmm.
And we can understand really our home planet and other planets, and start to understand what a planet actually is, and the conditions for life, and what kind of cool processes are out there.
Yeah.
And one of the paper we were discussing, is there still plume activity on Mars? We
Mm.
are doing now calculations with this mission. We will be able to observe the change in gravity field due to the plume. And
Mm.
this,
The
and we
plume.
would
When you
see.
say plume, do you mean the pushing up from below or the actual
Yeah,
volcano?
think lava lamp.
Oh,
So
it's a
you have
level.
a lava lamp, and you heat it up from below, and you get a blob of material that flows
Yeah.
upwards. Something
Is
similar
that still
happens
happening?
in
Yeah.
the interior of yeah, and this motion, this what we call
Mm.
mantle convection, is that still happening on Mars?
Mm.
I think it's plausible, and I think it really is there. There are evidence on the surface. We have a lot of these volcanoes, which is the
Mm.
end part of, you have the blob pushing towards the crust, and you get volcanoes.
Mm.
But that it's actually still happening, I think yes, because if you interpret the data, it's out there. But we can't say definitely, so we need this mission to actually observe it, and
Right.
then we would be the first to observe mantle convection on another planet.
Wow. How cool is that?
Yeah, that I think is awesome. Yeah.
Where does the funding come from? Is it government funding for you guys, or is it it's always a mix between business as well, I guess. But
Yeah. So I'm new to this a little bit, but so ESA is pitching in a lot. So building of the satellite, doing some research.
mm,
So that's related to the M class, if it would be selected. But
mm,
of course, you also are starting to talk with industry. Would this
right.
be interesting? And especially, it would be a cool precursor for quantum technology. If you
Mm,
can show,
mm,
look, I built this quantum accelerometer, I fly it to Mars,
mm.
you would be selling accelerometers everywhere, I would
So you
assume.
need to get you got to get the billionaires' attention as well. Then that's the yeah.
Maybe.
Maybe we should stop sending pop stars into space and start spending some money on some cool gravity research.
Yeah. No. And also the member states in Europe, it's the member states, so the
Mm,
countries, and we have to convince each of them. Look, this is science that is worthwhile for
mm,
the whole humanity,
mm.
and that's why we talk. We show the cool science, and
Yeah.
and that's where you guys can help. Talk to people about MaQuIs, about
Mm,
planetary sciences, about space engineering, because it's not a billionaire hobby. It's something where whole humanity can explore their existence, can
mm,
explore new processes, can learn about what a planet is, what
mm.
life is, what are we alone, is a big question that
Mm.
we can
Who
start.
doesn't want to know that? At the very least, who doesn't want to know that? You know.
Well, we should know if we're alone, and then be very quiet at the
And
job.
then exactly. I want to
I
be the
watch Three Body Problem too
yeah. I
much.
don't want to be. I also don't want to be the three body problem faster. That was I actually really I started reading the book. I quite enjoyed the book of that. But
Yeah,
the idea I keep picturing of us as Pigpen from the old Peanuts cartoons, where
uh,
it's just like the planet with like a black fog over it, where everyone's like, yeah, I don't want to be. That's a stinky
yeah.
looking planet. So
Yeah.
don't wake the wraith. Indeed. Bart, I'm going to let you go because I'm sure you've got things to do, and by the sound of it, you've got too many things to do. I don't know how you have time to do this, but I am going to, if you don't mind, if I haven't ruined it for you already, I would love to have you back for like an update on how things are going and stuff at some point, because this is amazing.
Of
This is
course,
so much
of course.
fun.
Yeah.
I will put.
We can talk about isostasy then.
Yes. In fact, we could do. Yes. In fact, let's just put that on the books now because we've got a whole other thing. Yeah, it's true.
Okay.
So look, any final words, anything you want people to know or to go to or to, I'll put stuff in
No,
the show notes, but yeah.
I just want to thank you, David and Agnes, for this opportunity. It's
So
really
much
nice,
fun.
and I like this type of talking about science.
Oh,
You
so
can
do
be
I.
you can put the personal touch there, and just the enthusiasm of what we're doing. And we're just also people that have ideas, and are just trying our best to look out and understand what we're seeing.
Yeah. Well, and share it too. Like, it's just
And
you.
share.
I think by seeing people get excited about this stuff, like, I love this. I don't understand why everyone isn't fascinated about this all the time. Like, I don't, so it's like every week I love the idea that I get to dive in, do a little research, and then get to talk to people who are doing this stuff, and hopefully get a little bit more of an understanding. And judging by the number of people chatting here, I can't keep up with it. It's fantastic. So I'll just make sure there's no other final questions, but I think we are more than used up your time at this point. So look, thank you, everyone. Thank you, of course, to Bart. And I will say, until we geek again, be brave, be kind, be brilliant, cheerio, and huzzah. Cheers. That's the